Hello, and welcome to the Chapter 2 extra video. And this one doesn't necessarily go along with our book, but the things in here I think are important for all of you to know, and hopefully you find it pretty interesting along the way. This is dealing with problems with sets. And I don't mean we're going to list a bunch of problems and just do example problems with sets. I mean problems with the definition of set. So in this video, we're going to consider the set of all sets. Now this is a pretty scary beast because it contains literally every set imaginable, including itself. We'll encounter a paradox that results from this consideration. And finally, we'll understand why our definition of set is problematic, and we'll see, I'll at least tell you about how mathematicians fixed it. All right, we start our journey by considering S, the set of all sets. So with our definition of set right now, this is a perfectly okay thing to define, right? A set is just a collection of objects. And so what I'll do is just collect all those objects which are themselves sets. Seems fine. I mean, it's a big scary thing, right? Think of any set possible, or think of any collection of objects. Well, that belongs to S. Well, S itself is a set, right? It's the set of all sets, but itself, it is a set. And so it must belong to itself. It must be an element of itself. Now that's pretty weird. We haven't encountered this yet, a set being an element of itself. So no problems yet, but that certainly seems fishy that a set should be an element of itself. Here's where it gets real interesting. We'll define this new set T to be the set of all sets which are not elements of themselves. So since we just invented this set S, we know that it's at least possible with our definition of set for sets to be elements of themselves. But in many of the cases we've seen, any example we've done with sets so far, we know that sets are usually not elements of themselves. And so we can say from what we've seen that, well, sometimes sets are elements of themselves and sometimes they are not. Mostly they are not, but sometimes it happens that they're elements of themselves. And so what we'll do is we'll collect all those sets which are not elements of themselves. We could actually define this with set builder notation if we want. T is the set of all sets A such that A is not an element of A. We can define the set T like this. And so this is a perfectly fine definition with our definition of sets. Now I ask you the following question. Well, first I'll state this this statement. So let P be the statement T is an element of T. And I ask the question, is P true or false? So what I'm asking here is it true that T is an element of itself, or is T not an element of itself? We know that any statement has to be either true or false, but not both. And so one of those two things has to be true. T is either an element of itself or it's not an element of itself. Now I'll pause here for a second to tell you, hey, if there's someone else in your domicile that you're living in your house, go find them and pose this question to them. If they're receptive to it, try and explain this to them and see what they think. Have a little argument with them. Is T an element of itself or not? I want you to try and answer that question by yourself first. In the next slide, I'll get at the answer. Now, I'm a little disappointed. I don't mind teaching online like this, but I'm a little disappointed that I can't have this discussion with all of you in class, because I always find this to be a really fun moment in class to discuss the statement P that I've concocted. Is T, the set of all sets which do not contain themselves, is that an element of itself or not? I always enjoy doing this in class, and I just enjoy talking about it. So this is why I try to get you to go out and discuss this with someone, because I want you to have some of that fun. But here we'll go through I wouldn't call it a solution, but we'll at least talk through the possibilities. So let's just assume it's true. Let's suppose P is true, and that would mean that T really is an element of itself. Remember how we define T, though. T is the set of all sets which do not contain themselves. Well, we just said T was an element of itself. So T does contain itself, and hence it must not be an element of T. That is, T is not an element of T. So that's the negation of P, right? P is false then. We assumed it's true. So we have both P, T is an element of T, and not P, T is not an element of T. We have both of those things. And we looked at this in a previous video, right? This is an example of a contradiction. This is never true. And so it can't be the case that P is true, because this results in a contradiction. Okay, so P is not true, so it must be false then, right? Well, let's see what happens if it's false. If P is false, then, not P is T is not an element of T. Okay, that seems fine. T is not an element of T. Well, that means that T is a set which does not contain itself, right? T is not an element of itself. But isn't that how we define T? It's a set of all elements which do not contain themselves. Well, and so by that definition, T is an element of T. So that is, T is an element of T. And so we have P and we have not P, right? P is both true and false again. We have P and not P, which is another contradiction. So if we assume it's true, we get a contradiction. If we assume it's false, we get a contradiction. And so is P true or false? Well, it's neither. Maybe we shouldn't even consider it a statement. This is a serious problem. It's a problem because no matter what the option is, we always get to a contradiction. And this is very bad news for mathematics. If mathematics is built off of logic and sets, which it is, and sets have these inevitable contradictions that come up with them, well, then mathematics has inevitable contradictions that come up in it that can't be solved. That is, mathematics would be inconsistent with this definition of sets, throwing the entire idea of truth or falseness out the window. We wouldn't be able to say anything's true or false with this definition of sets. So this is a very serious issue. So how is this resolved? Well, first I'll talk about who first posed this statement. And this is what's an example of what's called a paradox, something that it's neither true nor false. A paradox. And this is a named paradox called Russell's paradox. So like I said, this is named Russell's paradox after the mathematician and philosopher Bertrand Russell, who discovered this, came up with this idea back in 1901. So not even that long ago before someone figured out that, hey, this definition of sets as just a collection of objects is no good and will lead to contradictions. Here's a picture of Bertrand Russell, a dapper fellow there, smoking his pipe, thinking about sets. What a great guy. Love him. So he showed that, right, this definition of set leads to contradictions, and so mathematics is inconsistent if we use this definition of sets. So we got to throw away this definition of sets. It just doesn't work. We can't just say it's a collection of objects. It's just, in some way, it's just too simple a definition. And so the solution to this is something called the axiomatization of set theory, which means that really we needed to restrict the elements that are allowed to be in sets. And in particular, no set is allowed to contain itself with this set of axioms. So axioms are these statements that we sort of accept as true. We accept them as true and move on from that. And so there's a lot of different formulations for the axioms of set theory, but the most common one is known as Zermelo-Fraenkel set theory, or ZFC. And that's the most accepted axiomatization of sets that's out there. People can, discuss these axioms and debate the axioms all they want, but most people assume that the axioms are true. I'm not going to actually give you the axioms here, these set of statements that are accepted to be true, which define sets, because, well, it's just outside of the scope of this class. However, I at least wanted you to know that the definition of sets we use here has a lot of issues with it, but those issues aren't going to really come up come up in this class except in this video when I talk about them. It's fine for us to just consider sets as collection of objects. That's okay for the purposes of this class, but for mathematics as a whole, it's no good, and there needs to be a stronger definition of set. And so if you'd like, you can look up Zermelo-Fraenkel set theory, or as I said before, sometimes referred to as, they call this ZFC. So the Z for Zermelo, the F for Fraenkel, and the C for something called the axiom of choice, which is its own video, maybe even its own class. But that would be a fun thing to look up if you're interested in this topic. Okay, that's it for Chapter 2. Thanks for listening.